Okay. There is considerable number of auxiliary concepts which play a role in connection with the metric space. So, we will discuss various type of concepts, particularly the open wall, closed wall, open sets, closed sets, convergence, Cauchy sequence, etc., which will be used in the SQL or in the development of this functional analysis method. So, first let us see the what is the open wall. Open wall, let X t be a metric space, and X naught be a point in X. Let R be a positive real number, then open wall centered at X naught and radius R is defined as the set of those points in X whose distance from X naught remains strictly less than R. Then this collection will be termed as an open wall centered at X naught and radius R. The closed wall, in a similar way, we define and denoted by B delta X naught R as the set of those points in capital X, where X d is a metric space, such that the distance from X naught is less than or equal to R. The sphere, we denote this by S X naught R, that is the sphere centered at X naught, and radius R is the set of those points of a metric space X whose distance from X naught is exactly R. So, here we have a metric space, say X d, and X naught is a point in X. Then if we draw a ball around the point X naught with a radius R, then all such point which lies within this is the open wall, which includes the point of the boundary also closed wall, and the points lying on the boundary only we call it as a sphere. Now, obviously, this is clear from this definition that the sphere is nothing but the difference between closed wall minus open wall minus V X naught R. Okay. This is what we get the sphere. Now, we already have a concept in R 3, the concept of the open wall, concept of the closed wall, and concept of the sphere. The open wall is the centered X naught and radius R, is as usual in sphere, and we know that if R is a positive number or radius is non-negative, is positive, then with centered X naught and a positive radius, the sphere cannot be a negative, wall cannot be a cannot be empty. So, this concept is available in R 3, but since we are dealing with the X d, so the similar concept for the open sphere, closed sphere and the wall is not available in a general metric space. That is, we cannot claim that a sphere with center X naught and positive radius will always be non-empty. It may be empty also, depending on the metric which we are using. If we take the metric D as a discrete metric, then the sphere centered at X naught and say radius 1, this will be the set of those points X belonging to capital X whose distance from X naught 2 x is 1, that is the set of those points whose distance under the discrete metric is 1 is nothing but the all the points which is different from x naught, that is the entire space. But if we take is not empty, but if we take a ball centered at x naught and radius 1 in a discrete metric D, then we get the x naught which is strictly less than 1 comes out to be an empty set, because there are no other point except the x naught itself available in this class. So, this becomes empty. So, this type of difference is available in a general metric. So, while we enlarge the concept, we should be aware about this thing, that whatever the properties are enjoyed by the ball and the sphere in all three may not continue to hold good in a general metric space. We can take few examples where this, say, suppose I take the C, x is equal to set of complex number, and the sphere centered at 0 and 1, the set of those points whose distance from 0 is 1, then this is nothing but the set of all those complex number z where mod z equal to 1. Okay? And similarly, if we take the open ball, it is mod z less than 1 and like this. If we take another example, say x is equal to c 0 1, set of all continuous functions defined over the closed interval 0 1, and suppose I take the point x naught as theta, the continuous function which is identically 0 along the axis of x, that is the set of all continuous functions, say theta denotes the continuous function which is identically 0, which is identically 0 on this interval 0 1. So, here this is the interval 0 1 and theta is lying here. Okay. Then the distance, the ball centered as theta and with the radius 1 with the set of those point x belonging to capital A C A B C 0 1, such that the distance from theta is less than 1. This is the open ball. So, basically because this is a function, so if we draw a strip around the point x, a strip which is of bits 2, length is 2, surrounding the axis of x, then all these points which falls within the all the functions which fall within this range will come in this class an open ball centered at theta and radius 1. Okay. So, these are the examples where you can have a concern. Now, if we go for a slight generalized form, then we say an open set which use the concept of the open ball. Let x d be a metric space, be a metric space, and M be a non-empty subset of x. Subset of x. We say x is M is, we say M is open in x, open if it contains a ball about each of its point So, a subset M of a metric space X is said to be an open if it contains a ball about each of its point. That is, if we have this metric space and here is our M, then this set is said to be an open. If we pick up any arbitrary point inside it, then one can draw the ball around this point with a suitable radius which is totally contained inside M. Then M is said to be an open set. Okay. The complement of this open sets is called closed. So, we define the closed set as a subset K of X, X D is a metric space, is said to be closed if its complements if its complement with respect to X, of course, in X is open. If its complement in X is open, that is the K complement which is X minus K is open. So, we define the this closed set as a complement of an open set. The epsilon neighborhood is defined as epsilon neighborhood. An open ball centered at x naught with a radius epsilon is called an epsilon neighborhood of x naught. So, a set of all the points whose distance from x naught remains less than epsilon, then those collection we call it as a epsilon neighborhood of x naught. And what do you mean by the neighborhood? Neighborhood we mean by a neighborhood of x naught NBD I am using, by a neighborhood of x naught we mean any subsets of x, any subset of x which contains an epsilon neighborhood of the point x naught. So, if we have say x d metric space, x naught is this, then this set say S will be a neighborhood of the point x naught if it contains a neighborhood around epsilon neighborhood of x naught inside it. Then we say this is a neighborhood of the point x naught. The interior point we define as a point x naught belonging to capital X is an interior point point x naught next is an interior point of the set M which is a subset of X if M is a neighborhood of x naught. What is the meaning of this is that let M be a set and x naught is a point. We say this is an interior point of the set M if there basically exists an open ball around the point x naught with a radius epsilon l which is totally contained inside M. Then only M will be the neighborhood of this. So, if such a point is available, then that point is called the interior of M. The collection of all such point x naught forms a set which we call it a interior set. Okay. So, interior of M interior of M is the set of all interior points, set of all interior point of M, set of all interior points of M, and it is denoted by either M 0 or maybe some author used to write INT M, interior of M. Okay. So, this is the concept of the interior points. Then we have seen the open ball, open set, closed ball, closed set. The every open ball basically is an open set. We have defined the open ball is the set of those points whose distance from x naught is less than r, but an open set is the collection of those points where every point is an around every point we can draw the open ball which is totally contained inside it. So, basically the open ball is also a open set. So, we can prove this result. Every open ball is an open set. Let us see how. Suppose we have an open ball centered at x naught and radius r. This is our open ball. So, B x naught r, here is the point x naught, okay. And this is our ball. Of course, this radius is r. So, I just take it like this, so that this becomes r. Okay. We wanted this to be an open set. So, it means if we take any arbitrary point by here, then around the y, if we are able to draw an open ball which is totally contained inside it, then we say each ball is a open set. So, let y belongs to an arbitrary point belongs to x naught r. Let r 1 denotes the distance r minus d of by x naught. Okay. This distance is complete here and r, and here this distance is by x naught. So, I am taking r minus d by x naught as r 1. Now, if I draw the ball centered at by and radius r 1, we claim that this ball is totally contained inside ball centered at x naught and radius r. Means all the points of this ball will be available inside it. Why? Because if we take a point say z, because if we take any arbitrary point z belongs to B by r 1, then what is its distance from x naught? Let this be a z point. Okay. So, this distance will be less than equal to d of x z by plus d of by x naught. This is equal to d of z by, what is the z by? This is less than equal to r 1, because the distance from any point by belongs to r 1, z is the point inside you are taking. So, this is less than r 1 then plus this distance is by x naught, but r 1 plus this is nothing but r. So, if we pick up any z point here in this ball, then its distance from x naught cannot exceed by r. It means all the points of this ball lies basically within this V x naught r. Therefore, this becomes a open set. Okay. So, every open ball is an open set. Similarly, the closed ball is a closed set, is a closed set. So, we will not go through like this. Okay. Now, we go for this some results again. Suppose x d is a metric space. Let x d be a metric space. Then the following results hold: empty set phi and the entire space X are open. Okay. Second, the union of any collection whether it is countable or uncountable of open sets is open. So, any arbitrary union of the open set is open, and third is the finite intersection of the open set is open. Of open set is open. So, we can prove this thing. First is empty set and X are open. This is obviously true, because empty set you can say there no point is available. So, we can assume all any point around it, one can draw the open ball which is totally contained inside it. And since X is a entire space, is a universal space that we are dealing with that. So, any arbitrary, if we take any open ball inside it at any point, it is definitely a point covering X. So, these two are the trivial things and we can show. The second part, if suppose G1, G2, Gn are open sets in a metric space X d, then we wanted to show that union of this G I, countable union or maybe an arbitrary union, is open. This we wanted to show. So, if I prove that around any point of this set there is a ball which is totally lies within this set, then we say this collection is an open set. So, let X naught be an arbitrary point in this collection. So, obviously, there will exist a sum j such that the point will belongs to this open ball G j, but G j is open. So, by the property of the open sets, there must be a open ball around the point x naught with a suitable radius which is totally contained in it. So, there exists an open ball centered at x naught with a suitable radius, say r, suitable radius such that which is contained in G j. Therefore, it will contain in the union of G I is 1 to infinity. So, this shows this is an open set. So, union of G I is open. Clear? The proof of the second, the finite intersection of G I is open, where G I's are open. So, again the same trick, let us take a point x belonging to the finite intersection of this, then x must be the point in G I for every I. So, this is say G 1, this is say G 2, like this. Okay. So, if we take a point x naught, which is available in the intersection part. So, x must be somewhere here, which is a common point of both G 1, G 2 etcetera. So, many things are there. So, now, x belongs to each G I and G I is open. So, there must be a ball around the point each x, which is available in G 1, then maybe there is another ball available in G 2. So, there exists a R 1 and R 2 such that open ball centered at x and radius R 1 belongs to G 1, open ball centered at x and R 2 belongs to G 2 etcetera. Is it okay? Now, if I pick up the R as a minimum of R 1, R 2 and so on, and draw the open ball centered at x and radius R, will it not included inside the countable union of G I, finite union of G I, because it will be the smallest ball available in all the G I's. So, it will be, so G I will be open. Clear? Here we have seen the only the finite intersection of the open set is open. I am not taking the countable or any arbitrary intersection, because the countable intersection of an open set need not be open always. Example is, if we take G I say equal to 1 by I minus n comma 1 by I, where I is 1, 2, 3 and so on. So, this is an open interval. So, it is an open sets, open ball. Now, if I find the arbitrary intersection of this, then what happens? This is nothing but the set containing only singleton point, that is 0, intersection of this. So, a singleton set cannot be a open set, it cannot include any ball around the point. Therefore, it is a closed set. So, what we conclude is that arbitrary intersection of an open set need not be always open. Okay. The same type of results also available in case of the closed. X and phi are closed, a metric space X D, X and phi are closed set. Second, intersection of the closed set is closed. Any arbitrary intersection of the closed set, arbitrary intersection of closed sets is closed, while the finite unions of the closed set of closed sets is closed. So, this we can prove in a similar way, because the complement of this must be open. Therefore, we can say that these results are basically the complement of the previous ones. Okay. So, I think it is clear or any doubt. Okay. Now, we have another important concept, the concept of the limit point or accumulation point. we define the limit point or accumulation point as limit point, or we say accumulation point. Accumulation point. Let us suppose X d be a metric space. Metric space and M be a subset of X. A point x naught belonging to X, it may or may not be, may or may not be in M, is said to be an accumulation point of M if is said to be an accumulation point of M or the limit point of M if every neighborhood of x naught includes at least one point of M other than x naught. Because if suppose x naught is a point of M and then it includes except x naught, then it will not be considered as a limit point. Okay. So, limit point of a set M means if we draw a ball around the point x naught and M is such, this is our M. So, whatever the neighborhood you draw around the point x naught, it must include at least one point of M distinct from x naught, then we say x naught is a limit point of this, otherwise we will not say limit point. Okay. So, sometimes even that point, if it is not available, then we can, it is a boundary point. In fact, the boundary point is the point which has a property that if I draw the ball around the point x naught, then it will include both the points of M as well as the point outside of the M. Then that point is called the boundary point of this. Okay. So, this one. Now, another important concept in this is our dense set. Dense set. Let us suppose X d be a metric space and M be a subset of M. Let M be a subset of a metric space X d. We say M is dense in X if the closure of M is X. What is the meaning of closure? M bar denotes the closure of M. What is the meaning of closure? Closure set, a set M together with its all limit points. A set M together with its all limit point is said to be the closure of M. Is said to be the closure of M, and we denote it by M bar. So, basically M bar is the M union of all its limit point, M union of all its limit point. So, this is the closure. So, what it says is a set M is dense in X means closure of this is X. So, if the meaning of this is that if this is our X d space and here is M, clear? If we say closure of M is X, it means if we pick up any arbitrary point X belongs to capital X and draw the ball howsoever small may be, then it must include the some point of M which is belonging to M. So, it means M and this X they are very close to each other, that is we cannot separate out these 2 points. Whatever the point x you choose and draw a neighborhood, it will definitely include some points of M. Then we say closure of this set M is x. For example, if we take x to be the real line or real number and say M is the set of all rational numbers, rational points, then any real number if you pick up and draw the ball around the neighborhood around the point, that real number, that is in open interval, it will definitely include the rational points. So, q bar is R. That is one. Now, we have seen in case of calculus the function continuous functions plays the role. So, here also the concept of the continuity is defined in terms of the over a metric space as follows. We take the continuous function, let x d n by d be 2 metric space, let x d n by, let us assume another d bar a metric, let x d n by d bar and this is end and by d bar be metric spaces, and T is a mapping from x to y. We say T is continuous, then a mapping T from one metric space to another metric space is said to be continuous at a point x naught belonging to x if for every epsilon greater than 0 there exists a delta depending on epsilon and the point x naught such that the when d bar of T x naught is less than epsilon for all x satisfying the condition that d of x naught less than delta. What is the meaning of this here? Let us suppose this is our x d metric space, this one is say by d bar metric space and T is a mapping from x to y. Then we say this is a continuous at a point x naught if the image of this is T x naught. Okay. So, if we draw a epsilon neighborhood around the point x naught, then corresponding to this neighborhood one can find a neighborhood around the point x naught with a radius say delta, such that the image of any arbitrary point inside this neighborhood will fall within this range. That is, the T of x comma T x naught, the distance under d bar will be less than epsilon provided the point x and x naught satisfy this condition, or epsilon is chosen, then correspondingly you can choose the delta. So, that image of every point inside this neighborhood of the x delta neighborhood of x naught will fall within the epsilon neighborhood of T x naught. Then such a operator, such a function, we call it as a continuous function. Okay. And if this result is true, if T is continuous at every point of x, belonging to capital X, then we say T is a continuous function from x to y. T is continuous over the entire range x to y. Okay. Now, there is another definition of the continuous function in terms of the open sets, and that definition is given in the form of theorem. what this theorem says is a mapping T of a metric space X of a metric space X D into a metric space say by D bar is continuous if and only if the inverse image of any open subsets of Y is an open subset of X. Let us say what it says is that if T is a mapping from X to Y, X to Y d bar, T is a mapping from this to this, and then this mapping is continuous if the inverse image of any open subset of Y is an open subset of X. So, suppose if I take this S which is an open set and corresponding inverse image be say S naught. Okay. This is so, what is this says is if the inverse image of this open set is open, then T will be a continuous function, and vice versa if T is continuous, then inverse image of open set will be open set. Okay. The proof is like this. So, let us prove with the one assuming first T is continuous, and then we will show the inverse image of an open set is open. So, let T mapping from X to Y be a continuous function, be continuous. Okay. Now, we want the inverse image of open set is open. So, let us take S which is a subset of Y be a open set in Y, open set of Y. Okay. Let S naught be the inverse image of this, let S naught be the inverse, here S naught I am like this. Okay. Let S naught be the inverse image of S under T. We wanted to show S naught is open, is a open set in this. Okay. So, there may be two cases. If S naught is empty, is an empty set, then obviously it is open, because every empty set is open. Second, if S naught is not empty, then there must be some point. So, X naught is a point available in S naught. Now, we want this S naught to be open. So, if I prove that there is a neighborhood around the point X naught which is totally contained in S naught, then it is open, because X naught is an arbitrary point I am choosing. Okay. Now, X naught is a point in S naught which is a subset of X. T is a mapping from X to Y. So, this implies that T X naught must be a point of Y. Okay. Clear? T X naught will be point. So, if this is the point say X naught, here is this is say Y naught which is T X naught is a point. Now, S is open, S is open. So, around the point Y naught we can get the epsilonal neighborhood of Y naught which is totally contained inside it. So, since S is open, so there exists a neighborhood around the point Y naught with a radius epsilon r which is totally contained in S. clear. Now, T is continuous, T is continuous. So, by definition, if we take any epsilon neighborhood of by naught, then there will exist a delta neighborhood of x naught, say this is our n naught, whose image lies here. But so, there exists a delta neighborhood, say B of x naught delta in S naught, which is whose image will lie in the neighborhood of B by naught epsilon, clear, B by naught epsilon, open. Now, this is our clear. Now, S is contained, this neighborhood n is contained in S, n naught is image of S naught is S inverse image, and there is a neighborhood n naught which contained in S naught. So, we can say that this x n naught is contained in S naught, because S naught is an open, it is a open set, is it not. So, it will come to the open set, because the image of this, when you take this point T, the image is already we are taking S naught, and there is a neighborhood n naught which totally contained inside it. So, this inverse image S naught will be an open set, okay, lies in this. So, S naught is open. Is it clear or not? Now, conversely, in a similar way we can prove. Conversely, it is given that inverse image of the open set is open. So, conversely, given inverse image of an open set, no, conversely given inverse image of open set, inverse image of open set is open, that is given. So, what is known is that if we take S, T is a mapping from x to y, and this is our open set, here is also open set, the T is a mapping, inverse image of the open set is given to be open. We wanted T to be a continuous. So, what we do is that take any arbitrary epsilon here, x naught belongs to x naught, the image will be say by naught. Okay. Now, if we take any delta neighborhood of this, which is totally contained inside it, the image of this will be fall here, because T is given to be continuous. So, for a epsilon greater than 0, there exists a delta, such that d bar of T x naught is less than epsilon whenever d of x x naught is less than delta. Is it not? That we wanted to prove, which obviously follows from here, because if this is open, take a ball which is a epsilon neighborhood of this, an open ball, the image of this will be delta neighborhood here, clear, and since S naught is open, it is already given. So, this is totally contained in it. It means basically we are taking an epsilon neighborhood is given, then we can find a delta neighborhood whose image is lying here. So, T becomes continuous, is it not? So, that way we can find this thing. So, this is very interesting concept of this continuous function, and which will be used in a frequently many times. Then next concept which come from convergence part. Convergence of a sequence in a metric space. What is the meaning of the convergence of sequence in metric space? Just like a sequence x n, we say in sequence of the real number or complex number, when it converges, it means there exists a some point a or converges to x if for epsilon greater than 0 we can find n. So, that difference between x n minus x goes to 0 when n is sufficiently large. So, there is a real line. So, one can identify the point here, limiting point here. Same concept we generalize it for here. We say a sequence x n, in a metric space, x d is said to be convergent if there is an x, a point x belonging to capital X, such that the distance between x n and x tends to 0 as n tends to infinity, It means the difference between x and x, if it is a real sequence, or in general if it is a arbitrary mid class, then the notion of the distance between x and x under D, it must go to 0 as n tends to infinity. Clear? Then we say this sequence is a so existence of x is must. If x does not belongs to the class, then the sequence will not converge. And for example, if we take x to be 0 1 and if we take a sequence x n to be 1 by n and d x y, if we define as mod x minus y, then we say this sequence 1 by n, though it goes to 0, but because 0 is not available in it, then we say this x n does not converge to 0 in this metric space x t, in this x t. So, the point which is limiting point is must be available in x t, that is what we wanted for it. Okay. So, I think this is okay. We can go next time what is the concept of this bounded sequence, another later. Thank you.